Physics students, good afternoon. Mr. Fugit here. In our video today, we're going to be looking at a few problems for your review on test number 4. Test number 4, as a reminder, covers over Unit 5 on uniform circular motion, universal gravitation, and Kepler's laws of planetary motion. Specifically in this video, we're going to be looking at problems 3 and 4, which cover a little bit on g-force, as well as a little bit on our equation for universal gravitation. As a reminder, if you need a copy of your review or a copy of the key to the review, those are both posted on Canvas, either on the front page or on the Unit 5 page. So I will go ahead and read problem number 3 for us, and then we will get started. Problem 3 says this: a fighter pilot takes a sharp turn in their fighter, which is going 370 meters per second. The turn is circular and has a radius of 820 meters. What g-force is the pilot subjected to? So here, this is test number 4 review. We are looking at problems 3 specifically. And if you are looking for some help on problems 1 and 2, make sure to check the other videos that are available here on YouTube. So problem 3 says this: we're looking for a g-force, which we do have an equation for. G sub 0 is equal to our centripetal acceleration divided by g for a local area. Here we're looking at the Earth. So remember, when we talk about g-force isn't an actual force in the same way we approach other forces. G-force is a ratio of accelerations. It's really an acceleration that a person or object is subjected to. And the reason that we're interested oftentimes in g-force is that g-force helps us understand how humans might be affected if they are taking a sharp turn and moving at a very high rate of speed, which can affect their bodies and can oftentimes be dangerous depending on the amounts of g-force that they're experiencing. So here, the first thing we need to do, since we know a lowercase g for our local area, which is the Earth, we really just need to find the centripetal acceleration. So to do so, we have an equation. A sub c is our velocity squared over the radius of our circle, or what we call the radius of curvature, or we are sweeping out a radius of a certain distance. So here we'll take our velocity, which is 370 meters per second. And we are in a jet, so we're moving very quickly. And that velocity will be squared, divided by the radius of the circle we move in, 820 meters. Now again, that value doesn't mean that our pilot is just making circular turns in the air. What it can mean is that our pilot is traveling in a straight line, and then he or she makes a turn. And again, we're not maybe making a full circle here, but the radius of the circle that we are kind of sweeping out is 820 meters. So it's a very wide turn. So we'll take our values, 370 meters per second squared, divided by our radius, if you will, 820 meters. And we get a value for our centripetal acceleration of 166.9. So I can go ahead and round that to 167 meters per second squared. And now that we have that value, we can plug back into our equation to find the g-force. So g-force is g sub 0, which is equal to our centripetal acceleration, 167 meters per second squared, divided by 9.81 meters per second squared. So we'll take the value that we just determined and now divide by 9.81. And we end up with a value of 17.02 G's. Now again, when we talk about g-force, it's not a force in the way that we understand other forces, which is why we don't have a unit of newtons assigned to it. And what this value means, 17.02 G's, is that our pilot is being subjected to 17.02 times the regular acceleration due to gravity they experience on the Earth, which is a pretty high amount of G's. If you look at the chart on your review, again, this isn't always applicable. Different humans have different limitations in their body. There's also special training, oftentimes the pilots will do to help raise their ability to withstand g-forces. They can also wear specialized equipment. And it also depends on how long you're subjected to this amount of g-force. Here, this looks like it might be in the range of something that would be a little bit dangerous. It's probably teetering on the line of what the pilot could reasonably be subjected to. This might cause definitely some dizziness, possibly even loss of consciousness. So in order to make this a safer turn, we could maybe either suggest the pilot would either lower their velocity at which they make the turn, or maybe increase the radius, make it a wider turn so that it would be a safer amount of g-force as they make this turn. But again, hopefully this gets us moving in the right direction for how to solve for the g-force on a person, given how fast they're moving and the type of turn that they make. So now we'll move on to problem number 4. I will read it for us. Problem number 4 says this. Assume the mass of the sun to be 1.99 times 10 to the 30th kilograms. The mass of Saturn to be 5.68 times 10 to the 26th kilograms. And the distance between the two objects to be 1.43 times 10 to the 12 meters. Part A of question 4 asks us, what is the force of gravity between the sun and the planet Saturn? So here, this is problem number 4 on our review. And we're looking to find the force of gravity, which is again a force of attraction between any two objects with mass, between the sun and Saturn. So, if we're looking at the force of gravity between these two objects, we can use our approach for Newton's law of universal gravitation. Our constant, big G, multiplied by m1 and m2, which are the masses of our two objects, divided by d squared, the distance between our objects squared. So now, I'm just going to take the numbers that we were given and begin to plug them in. So our constant, big G, is 6.67 times 10 to the negative 11. As you've seen in class, oftentimes we use the capital E to represent our values in scientific notation. Then we have the mass of our two objects, the sun and Saturn. For this scenario, it's not going to matter significantly which one we call M1 and M2. I'll go with the sun's mass because it's the first one given to us. So 1.99 times 10 to the 30th kilograms. And the mass of Saturn, 5.68 times 10 to the 26th kilograms. Just fit that in. And then we have the distance between our objects, center to center, which would be 1.43 multiplied by 10 to the 12 meters. And as we looked at in class, something I've suggested is to add a second set of parentheses to our denominator, just so we can see we need to square our denominator before we tell our calculator to divide by that denominator. The order in which your calculator processes these functions is very important. And as we've talked through, one of the major issues we can often face in solving an equation like this is making sure we plug things in appropriately. So if we use parentheses for each value in our equation, as well as a second set of parentheses in the denominator, that's usually going to set us up to be successful. So let's go ahead and plug this in. 6.67 times 10 to the negative 11, multiplied by 1.99 times 10 to the 30th, multiplied by 5.68 times 10 to the 28th, and then we'll divide by our denominator, which we need to square first, 1.43 times 10 to the 12th, squared. We should get a value that's going to appear to be pretty large. I'll double check that with what we have here. 6.67, even the negative, good, 1.99, 5.68 times 10 to the, and you'll notice I made a mistake here. The mass that we are given for Saturn is actually 5.68 times 10 to the 26th kilograms. Again, very easy to make a mistake. I'm often prone to doing that myself if I read through something a little bit too quickly. This should be 5.68 times 10 to the 26th kilograms. I was getting a value a little bit higher than I thought I should have, so I'll go ahead and change this just quickly. 6, there we go. Divide by 1.43 times 10 to the 12th squared. Good. Good. So now I'm getting a value that appears to be what I solved for just a moment ago as I was checking through some of these values. We get a force of gravity between our two objects of right at 3.69 if we round up. We can write this as E, or times 10 to the 22nd power newtons. Now again, as we've talked through, one of the most common mistakes we can make is making sure we plug things in all appropriately, especially with all the numbers that we're dealing with. Here, I made a just easy error. I substituted the 6 there for an 8, which I can make. So it's always helpful to make sure you double check your calculations so that we're not making those small errors. Okay, now that we've solved part A, we'll look down to part B. It says this: use this to determine the value of both the orbital velocity and the orbital period of Saturn. So one way that we can do that is this. We need to find a velocity, and we have an object that's moving in a circle. So that probably means we're going to have to use our equation for centripetal force, mv squared over r. Now, as we've showed throughout this unit, when we have objects that are moving in orbit, planets, satellites, moons, things of that nature, the centripetal force is actually going to be a force of gravity. We usually have a large center object, like a planet, could be the Earth or the Sun, and something in orbit around that large planet. And so, usually, when we have something in orbit, it's going to be that force of gravity that causes the circular motion around that centralized object. So, what we can do here is we can actually set our force of gravity equal to our centripetal force. So what I'm going to do is this. I'm going to say that here, our force of gravity is going to act as our centripetal force, which means it will equal the mv squared over r equation that we use for objects that move in circles. Now, because my numbers are really large here, what I'm actually going to do is I'm going to solve this equation just using variables for my velocity, and then I'm going to plug things in. So here's what I'm going to do. I'm going to set fg equal to mv squared over r, and then I'm going to solve the equation for v. So in order to get v by itself, I need to first maybe get rid of my denominator, which is the radius term. So r, I'll multiply that up to the numerator, and for simplicity's sake, I'm just going to erase that from this side of my equation. Now, I need to get rid of the other things around the velocity term. So I'll divide by the mass, m. So m over n, those will simplify out. And now I just have the velocity term by itself. Well, almost. I need to take a square root. I'm going to take a square root of both sides of my remaining equation. The square root of v squared is actually going to simplify down to be just velocity, and that velocity will be equal to the square root of the radius of our circular path multiplied by the centripetal force, which is here the force of gravity, divided by the mass. Now, if it is easier for you to go ahead and plug values in first and then do all the algebra and rearranging and multiplying and dividing and square rooting second, that is fine. Usually I like to go ahead and solve for the variable I'm looking for first. That way I can plug all my values in to one equation and don't have to do any rearranging after that. It's usually a little bit easier for me if I'm just looking at variables versus all the really, really big numbers. Okay? But again, your approach is up to you as long as we feel comfortable with getting to the answer that we need. So it is important for us to pay attention here. We do have a value for mass. But remember, we have two masses here, the sun and the earth. So if we're looking for the velocity of the object moving in a circle, which is going to be Saturn here, going around the sun, we're going to use Saturn's mass here, because it's the object that's moving in a circle. So let's go ahead and plug in the things that we know. Our velocity v is equal to the square root of r. Now r is a radius. Be careful here, that's not the radius of the planet itself. It's the radius of the entire path of the object moving in a circle, which is the distance from the sun out to Saturn. So the r term is going to be our radius, which is the distance between objects, 1.43 times 10 to the 12 meters. Oop, not second. Again, very easy to make that mistake. 10 to the 12 meters. Close those parentheses. And then we will multiply by the force that we saw for in part A, 3.69 times 10 to the 22nd power. Newtons. And then we'll divide by the mass of our planet Saturn. That is the object moving in a circle. 5.68 times 10 to the 26th power. Kilograms. And then we will take a square root of that entire function. So we have 1.43 times 10 to the 12 meters, multiplied by 3.69 times 10 to the 22nd newtons, divided by 5.68 times 10 to the 22nd kilograms, and then we'll take a square root of our value. We get about 9,634, which looks about what I found here. So 9,634, that is a velocity. We have units of meters, kilograms, and newtons, so our standard units. So 9634 meters per second. So a little bit of work to get to our velocity. The main key that we need to see here is this. When we have an object that is in orbit, a planet, a satellite, a moon, the connection here is this. Our force of gravity is acting as our centripetal force, which means we can take that force, once we know it, and set it equal to our equation for centripetal force. Again, this relationship will not always and forever be true. It's true here because gravitational forces are acting as our centripetal force. Now again, we haven't actually solved for everything we need to. The last part of this problem is looking at the orbital period of Saturn. But now that we know its velocity, we also know the radius of its circle, we actually have a way to relate those terms. The velocity of an object moving in a circle is 2 pi multiplied by the radius of its entire circular path divided by the time period. So the period term by itself, which is what I would probably do here, I can multiply my time period up to the numerator of my equation. That will cancel out the period term on the right. And then I can divide by my velocity term on both sides of my equation. So the velocity term will cancel out on the left. And I'll now be left with an equation for the period. 2 pi times the radius, which is the radius of its entire circular path, divided by the velocity, which we just found. So here we go. Period is 2 pi multiplied by, again, that's the radius of the entire circular path, which is from the sun all the way out to Saturn. That is not very well centralized. There. So again, that distance from the sun out to Saturn is also the radius of Saturn's orbit. So 2 pi times the radius, 1.43, times 10 to the 12th meters. Oop, not second. 12. There we go, meters. Divided by its velocity, which we just found, 9,634 meters per second. Now we can plug our values in. So 2 pi multiplied by our radius, 1.43, times 10 to the 12 meters, divided by our velocity, 9634. We're going to get a period, and that's going to be a really large number. Remember, the units are going to give us some context. So I'm going to write down what I see, 932, 597, 977. Okay. And usually not the most accurate thing to do, just write out all the values because of the ideas of significant figures. We don't actually know that all those numbers are perfectly right. One thing we can do here is make some conversions, right? Because this is a really big number, but it's in seconds. So we don't know how long that number is in something like minutes, or hours, or days, or months, or years, right? So what I'll do here is a little bit of converting. So if I divide this by 60 seconds per minute, still really big. Divide by 60 again, still really big, because there are, again, 60 minutes in an hour. Divide by maybe 24 hours to days. Still, so if I convert this to days, I get approximately 10,793 days, which again seems also really large. You will divide that by 365, not roughly, but there are 365 days in a year. Now I get a value of 29.6 years, meaning that it would take Saturn roughly about 30 years to make one orbit around the sun, which is right about the value that we would need, or the value that we can actually just look up. Right? But again, not that the number in black is wrong, it just doesn't really give us a good context for what the time period really is. But if we say something like 30 years, that at least makes a little bit more sense to us. So, all that to say, hopefully that gets us moving in the right direction on problem number 4. We looked at finding the force of gravity between Saturn and the sun using Newton's law of universal gravitation. And then we used our relationship of forces of gravity may be equal to our centripetal force when we have an object moving in a circular pattern from an orbit, planetary motion, or not just planetary motion, but satellites or moons around a planet. But any type of orbital motion, we have centripetal forces that are going to be our force of gravity. We set those equations equal, did a little bit of deriving to find our velocity, and then some more work to find our period. But hopefully that gets us moving in the right direction on question 4. Remember, if you have questions, make sure that you are doing the best you can to get them answered from the resources you have available here, asking them in class, and then checking these on Canvas as well. Hey, good luck.